Hey there, Math 126 fans. I thought I would go through a kind of a quick run through of Practice Exam 1. Again, there's nothing special about the practice exam except that I just wanted to grab questions that were on our four big topics. The first topic is lines and planes. That's what's going to be on page 1 of your test. But let's just go through the practice exam. And I just want to go more through thought process. Like the moment you see this, let's just recap. Find parametric equation for the equation of a line. So you should immediately be thinking, I need a point and I need a direction. So you should be writing this plus t, t, t. And you should have this strategy of trying to find a point, trying to find a direction. And look at, we're doing the intersection of two planes. And so we have a very clear strategy, which is to find 2 points. So back when we were talking about this, I said, point, find a direction. If it's the intersection of 2 planes, try to combine them. In this case, I think what I would do is I would subtract because the x cancels side by side. So that gets you down to 2 variables. And then you can fairly quickly find 2 points. I mean, we're almost done. How do we find 2 points? We pick a value of y or z, and then from that we get a corresponding other values. So I usually pick what if y is 0, and then from that I solve for z, which has to be 4, and then from those two I plug them in up here and I see that x has to be 6, and then I double check both. Similarly for the other one, I say, well, how about z is 0? It doesn't have to be 0, it can be something else. You get y is 5, you plug it in, you get this is 5, and then you're done. You pick one of the points, it doesn't matter which one. I'll pick 6, 0, 4, and then you get a direction vector by subtracting. So you do 5 minus 6 is -1, 5 minus 0 is 5, 0, -4. It is that fast. So you do need to remember that you're looking for a point and a direction, but it's quick. Okay, let's keep going. So I'm just going to kind of do that same. You can follow up with more detailed questions. There are many other correct equivalent answers. Many students ask me about that. As long as your vector is parallel to this vector, and as long as your point is a point that works in both. That's how I grade it. Okay, let's keep going. The next question says, find the equation of the plane, or it says consider the plane that contains this line and find where it intersects the y-axis. So the moment you hear the word plane, you should be drawing this picture. You should be thinking, I need a point and I need a normal. And you should have the strategy of, maybe I can find 3 points. I'd be filling in these points, x minus blank plus y minus blank plus z minus blank. And they already told me one of the points, and so I'm halfway done for 2. The key word here is that it contains this line. So this line is on here. And that means I can actually extract a few things. But the strategy now becomes find 2 vectors that are parallel to my desired plane and do their cross product, and then we will be done. So that now is the strategy. So my thought would be, well, I already have a vector that is parallel to the desired plane, and that's this vector 5, 1, -1, because that line is on the plane. I need another. So that's kind of the challenge here. But I already have a point on the plane, this point 4, 4, 2. So the question is, can I find another point on the plane? Well, I don't have many places to look. All I have is this line. Can I get a point from that line? Yeah, how about when we plug in 0, we get 0, 3, 4. I can get the vector AB. That will be another vector on my plane, and then I can do the cross product. So this is going to be, let's say we're doing AB, -4, -1, 2, and then I can do a cross product. So you definitely want to practice this going into the exam. You want to be comfortable. You want to have a routine for checking. We've done this a lot this term, but now is the time to sort of recap. So this is going to be 1 minus 2i minus 4 minus 10j, and then -4 minus -5k. I don't know why I wrote it twice. -1 6, 1. So I'm going to do negative 1, 6, 1. Okay, so that was the game we were playing back on exam 1. Again, I should have checked. We need to check that this is perpendicular to this by doing a dot product, but I can see that it is because 4 plus 2 is 6, and then minus 6. We need to check that it's perpendicular to this. Negative 5. Okay, that's perpendicular. So you want to build in this check. The last part of the question is, when does it intersect the y-axis? Now, if you're on the y-axis, that means that x is 0 and z is 0. So that's how you finish the question, is you say this is 0 and this is 0, and you solve for the corresponding y. I think that's fairly quick. So you get 4, when I plug in a 0 here, plus 6 times y minus 4. Plus negative 2 equals 0. Let's see, that gives you y minus 4 is negative 2 over 6. Just doing some quick arithmetic, and I know I'm going off the screen. And then you get y has to be 4 minus a third. 4 is 12 thirds, so it's 11 thirds. And that's our little point here. So there's a quick recap, an example of an old exam where we do that. All right, let's move forward. The second page of your exam is going to be about polar and polar double integrals, because we haven't been tested on that yet. So that's more back to kind of the chapter 15 stuff, which is knowing your region. So all of chapter 15 was about understanding a region. This one said inside a circle of radius 3 and above the x-axis. So let's get this region drawn. And you have 3 different ways to describe that. You can do it in terms of y, you can do it in terms of x, you can do it in terms of polar. Now this question did ask in terms of y. Technically that's not a polar question, but let's do it real quick. If I label this y, what's the biggest and smallest y can be? 0 to 3. And you're always doing it in terms of this outer bound. And then based off of y, what's the left and the right? Well, that would be taking the circle equation, radius 3, so this is 9, and rearranging it in the form of what is x based off of y. So this would be negative the square root of 9 minus y squared, positive the square root of 9 minus y squared, sine of x squared plus y squared, dx dy. Okay, the question was actually asking about polar, which is the nicest way to do it. So in terms of polar, the smallest angle you can get is 0. The biggest angle you can get is pi. And so you say the integral from 0 to pi. And then because it's a circle, no matter where you stand, you're going to walk out. So 0 to 3, 0 to 3, 0 to 3, 0 to 3. So it's going to be 0 to 3, and then you change the rest to polar. So it becomes sine of r squared, r d theta. Okay, that's all that was, but you need to know that. Okay, the next question was a polar problem that says find the area. So back when we talked about we never learned how to do polar areas when we talked about polar on 124 or 125 here at UW. And so the start of this question is to say, I want to do the double integral of 1. And you did that in the homework. That's how you can use a double integral to find an area. The rest of the question became describing the region. Now I can see when I look at the region, it's between these angles. And so I would say negative pi over 2 to 0. Or you could say 3 pi over 2 to 2 pi. So I think that's one consideration. And then from that, we need to know the other curves. Now, one of the curves is just a circle of radius 2. We can see that here. The other one they give a formula for. So as you walk out, that's what I encounter on the inside. And then I encounter the 2 on the outside. So this should be like this. And then it becomes r d theta. The rest of the problem becomes calculation. I have had a few students ask about that, so let's just run a step in. You're integrating with respect to r, so this is going to be negative pi over 2 to 0, of 1/2 r squared, 1 plus sine of theta to 2 d theta. And the rest is going to be calculation, but let's keep going a little further. We're going to plug in the 2, and so that's going to be 1/2 of 2 squared. I guess let's write it. I don't want to skip steps and leave confusion. You just keep going. Minus, and then you plug 1/2, 1 plus sine of theta squared. So the challenge in this question, this old exam question, was right here. I mean, the setup was what most of the points were. So the students who did this got most of the points. To get the last couple of points on the problem, you needed to be able to finish this integral. And this requires expanding. So let's do it. So the integral from, so if you don't know how to expand that, you expand it the same way you always expand. So this is 1 plus sine of theta. Let me scroll this up a little bit. So we're doing this times this. We're monkey facing it out or foiling it out. Okay, so here we go. So negative pi over 2 to 0 of 2 minus 1/2. And let's monkey face this thing out. 1 plus 2 sine of theta, 2 because of the nose and the mouth. And then we have a sine squared. The way you integrate is you just then sweep across it left to right. This is just like doing algebra. You clean it up, and then you sort of look at what you have. So let's do that now. Let's distribute the 1/2, and let's sweep across and clean it up. So 2 minus 1/2 minus, I'm distributing this minus 1/2, so it's going to be a minus sine of theta minus 1/2 sine squared of theta. So when you see a string like this, you go, well, which things can I do? Well, this is 3/2, so I can integrate that. This is sine, so I can integrate that. So what's left is this one. How do we integrate sine squared? And that's from when we did this section. We said in this section you often get these trig integrals, and you need to know that when you see an even power of sine or cosine, you're going to do a half angle identity. So that's just part of that section. It's the downside of polar, but that's not really a big downside. So we have 3/2 minus sine of theta minus 1/2. And now we're going to do the half angle identity. 1/2, 1 minus. And there's a handout on my website about a review of trig integrals. It's a couple cases, but that's what's happening right there. At that moment now I can expand everything out and I have it. So it's yes, it's a little bit of a long calculation, but it's doable. My advice typically is to simplify as much as you can before you integrate. So it's worth taking an extra moment. I find, in my classes there's a little more angst about calculating, but we have to embrace it. We can do this. So at this moment, I would combine those two fractions, and then I can integrate. All of those are in my table of integrals, and I can evaluate. So I think I've addressed the main questions, maybe just for space. That's what's happening here. So I put those numbers together, made it 5/4. I integrated, and that's what the student was asking about. At the last, I plugged in my numbers. Okay, let's move forward. So then I have a Taylor polynomial question. Let's play that game a little bit. Pretty much when you get to this page, you know you're going to be taking derivatives, and so you just sort of gear up for derivative taking. So let's play that game and see how that looks. We have, since I'm about to do a whole bunch of derivatives, I would like to do this. Find the second Taylor polynomial. So I'd like to plug in 4 to that, which I think comes out to be a nice value, and then I'd also like to take its derivative, and I'd like to take its second derivative. So 3/2, 2x plus 1 to the 1/2 times 2, and the second derivative, and I should have done this, these 2's cancel. Okay, so now we're going to have 3/2 bringing that half down, 2x plus 1 to the negative 1/2 times the derivative inside, which is 2. Oh, the 2's cancel again. That's nice. And then we're going to plug in 4 to all of those things. Now, the square root of 2 times 4 plus 1 is the square root of 9, which is 3. So this is going to be 3 to the third, which is going to be 27. This one's going to be 3 times square root of 9, 3. So this is going to be 9. And this is going to be 3 over 3, which is going to be 1. Okay, so now we need to hang those on our clothesline. So the clothesline I'm talking about is this. So it's the number plus 1 over 1 factorial, which you don't need to write, x minus 4 plus 1 over 2 factorial. And you want to make sure you write all those things. Occasionally I have students leave this off and they're like, why did I lose a chunk of points? But that's exactly what we're testing, so don't leave that off. So 27 plus 9x minus 4 plus 1 over 2 factorial, or 1/2, times 1. X minus 4 squared. That's it. Then the question says to use this to approximate what the value would be when this in here is 9.1. That's kind of a goofy question. You would have to figure out, when is this in here 9.1? What's the x we're plugging in? And I think what you get, so subtracting 1, you get x has to be 4.05. And then it's asking you to plug in 4.05 here. Okay, then the last one asks you to do an error bound. Now, one question, natural question a lot of students ask is, what's the deal with this? How do I know what my interval is? The interval has to include your base, which is 4, and it has to include where your approximation is, which is 4.05. So that's the smallest interval you can use. To do this, we need, to do the Taylor's inequality, we need the next derivative. So we need the third derivative. What is this third derivative? Okay, let's write it down. So I'm going to just grab the second derivative and then come down and work from there. So the third derivative is negative 3/2 2x plus 1 to the negative 3/2 times the derivative side is 2. So we put absolute values around it, and we say what is the biggest the third derivative can be. Now, if I was doing this, I would cancel the 2's. The absolute values get rid of the negative, and so I would have 3 over 2x plus 1 to the 3/2. And then I'd ask myself, what is the biggest this can be if I'm only allowed to plug in numbers between here and here? Once I figure that out, I will finish the question by saying the error is less than or equal to m over 3 factorial x minus 4 to the 3. And I know at the very end of this question, I'll put in 4.05 here. Let me shrink that a little bit. So that's what we're trying to finish out. So there's really just one job to do, which is to say, what is the biggest this can be? Well, the biggest it can be is when the denominator is smallest. The denominator is smallest when you plug in 4, so you get 3 over, plugging in a 4 there, 9 to the 3/2. Ooh, that's nice, because it's going to be, square root is 327. So it's going to be 3 over 27, which is 1/9. So our final answer would be 1 over 3 factorial. The m would be 1/9, which is what this is. And then this altogether would be 0.05 to the third. And that gives an error bound for the previous part. Okay, on to the last question. So the last question is a Taylor series question. This is sort of typical for how these go. I tend to ask for the pattern first. This one jumps right into using the pattern. But here's what we would do. We would say we're substituting x to the 4th into the series for sine. So let's break that down. if you're struggling with this. So the sine series looks like this. -1 to the k, 2k plus 1 factorial, z to the 2k plus 1. So let's lay out what's happening. There's an x on the outside, and there's an x to the 4th on the inside. Done. Now it's a lot more user-friendly if I can clean that up, so let's do that now. This is the same thing as x to the 8k plus 4, and if I distribute that x all together, I get the sum. That looks like this. Okay, that one's done. Let's go to the next one. 4 minus x cubed. So I would like to factor out this. So I'm going to use the following series, which looks like this. That's the pattern we know. But I need to think about what goes in that slot. Well, I'm going to put an x squared out here, and I'm going to put a 4 here. Factor those out. So there's an x squared and a 4 out front. What does that leave in this spot? Well, let's see. It's going to be x cubed over 4. X cubed over 4. And then again, if I'm doing this, I would want it to be a little more user-friendly for myself. And so this is the same as x to the 3k over 4 to the k. And if I distribute that x through, let's write kind of the cleanest possible answer. It's going to be the sum from k equals 0 to infinity. The 1/4, I could make this. Yeah, let's make it as clean as possible. So I'm going to write 1 over 4 to the k plus 1. And then I'm going to write x to the 3k plus 2 from the 2 that goes in. So that's more of a notational thing. So those are the Taylor series for those two pieces. The question was then, usually I would add, if I was writing this question, I would have had this as a separate question. I would have had students give the patterns first. That's just more of my style. But this question said, I want everything up to the 10th power. So they're saying, okay, now that you have this, get everything up to the 10th power. How do we do that? We just start plugging in. We plug in 0, we plug in 1 until we get to the 10th power. So for the first series, let's write out for sine. If I plug in 0 to everything in there, I get 1 over 1. So just 1. X to the 5th. So I get x to the 5th. Okay, so we're not to the 10th power yet, so we keep going. So then what happens when I plug in a 1 here? When I plug in a 1, I'm going to get x to the 8 plus 5, which is 13. And 13 is bigger than 10. And so I've already made it. So I only had to plug in k equals 0 here. Anything beyond that, the exponent will be bigger than x to the 10. So that was kind of so anyways, plus other stuff, but we're truncating it because it only asked me to go to x to the 10. And now let's do the other series. The other series up to x to the 10, let's put in a 0. We get 1 over 4 x squared. So I just put in a 0 for k. Now let's put in a 1 for k. 1 over 4 squared x to the 5. And then the next one, 1 over 4 to the 3rd, x to the... So I put in a 1, that was 5. I'm going to put in a 2, so this is 8. If I put in a 3, I get 11. So at that point, I go beyond it. So that's what the question was asking, was to keep everything up to the 10th power. So if I was trying to write it all together, I would say this. I mean, I don't even care if students leave this separate, but it probably had them written together, I'm guessing, in that solution. Because 1 over 16, 16 over 16, so it probably was written like this. plus whatever this is. I should know it. Okay, so that's what that was, but the key steps are know how to find the pattern. And then the second part was be able to plug in a few numbers into the pattern. For the open interval convergence, we have to go back and ask, what did we plug in? Now, we plugged into x to the fourth to the sign, but there are no restrictions on sign. There are restrictions on when these things are equal. So basically, you have to figure out, did I plug into the geometric series? Yes, I did. What did I plug in? I plugged in x cubed over 4. And what restriction does that lead to? It leads to this, taking the cube root. Done with that part. Okay, the last goofy part is asking about the pattern. So the quick answer here is, if you had done the normal Taylor polynomials by taking lots and lots of derivatives, you would have eventually gotten to a term that looks like this. So it's not asking you to take 2024 derivatives. It's asking if you can find the term where the exponent is 224. This is a particularly challenging version of this question, but it's asking what is the number in this spot. And then from that, we're going to try to deduce what that derivative is. So I'm going to look back up at my pattern, and I'm going to say, do I ever get an exponent here of 2024? And when I look at it, I already know that the first one, that's not possible with the first one, because it's going to, well, let's not make assumptions here. But it's because it's going to be odd. I can already see this is going to be odd. So it's got to be the second one. But you could just try to solve both. So let me grab the two patterns and pull them down to our question. And say, all right, is it possible for either this exponent or the other to have 2024 here? And if I can figure that out, then I can figure out the number in front of it. And I can say the number in front of it has to match up with our other technique. Okay, so it's sort of a convoluted type of question, but it's a pattern question. So I'm asking, is it possible for this to be this? I actually already know that's not possible because you can't have an even equals an odd. But you could try to solve and you're going to get a fraction for k. So that's not possible. It's got to be a whole number of steps out. Okay, the next one. What about 3k plus 2? Can that equal 2024? Well, that would mean 3k is 2022. That is divisible by 3. Let's see what you get. 6, 222, 7, 4. Don't trust me. So the only way I can get this is when this is 6, 7, 4. And so we would put that in here, and now we know the number that goes in this spot. The number in front of x to the 2024 has to be 1 over 4 to the 6, 7, 5. That's the bit of logic. And that means these two things have to be the same. So the conclusion from all this is that 1 over 2024 factorial times the 224th derivative at 0 has to be 1 over 4 to the 675. And then you can multiply both sides by 2024 factorial. And you have this weird thing they're asking about. We'll do some more of that in class, but the main things you need in these questions, first is be able to find that pattern, be able to know you need to take derivatives, be able to set up polar regions, and then remember your lines and planes. All right, hope that helps.